Thank you for coming. We'll go ahead and get started. So today we're going to do something a little different. It might be confusing to me. Hopefully it's not confusing to you. So we're going to do the director's commentary version of a presentation. So this is a presentation I've done multiple times to user groups and middle school, high school people in other language communities, trying to understand what's the C++ thing doing. So this is, you want to know what C++ is, this is what I would say. And since you're here, you're not that audience, the material is relevant because I think this is something that we can talk as a community about how other people perceive us and how we can perceive us. If you've been doing the language a long time, there's probably some things that maybe you learned and you remembered and it's so ingrained in you that you forgot it. So that's kind of the purpose of this talk. So the language is actually a very simple language. People coming from other languages, a lot of the other languages, they're reference languages. They're doing dynamic scoping. They're not strongly typed. And all the other languages kind of look the same. And C++ doesn't look like those, so they assume C++ will behave like them, but it won't. So, we have static typing, lexical scope. We have a lot of things that we know to be true that are just not consistent with people coming from other languages, other domains. So in a nutshell, this is the director's commentary. If you came for the talk because you only know Python, but you want to know what's about C++, the slides are very rich. Take them home, they're free. Present them to your friends, hand them to your kids, whatever you want to do there. Maybe be inspired by it. But the director's commentary is kind of the thought where, why do I have the slides there? Why did I rank the importance of these concepts? And how did that go over? How did that go over in the various communities and the different people with different experience levels? So if you have these down, you are absolutely a professionally operating, high-quality code-producing C++ programmer. That's the stuff. There's no move semantics there. There's a lot of deep, dark corners that you could do if you wanted. That's not the vast majority of the world, and that's not the way you solve the vast majority of problems. So, hello world, we start out, there's main, does stuff, and we bootstrap, main begins, there's some setup that happens before, there's some shutdown that happens after. When main begins, the program begins. When main is over, the program is over, right? There's a little bit of setup and shutdown, but that's it. That in a nutshell, that's C++, all well-defined, very simple. So what other people are hearing is it's a scary language. There's all this undefined behavior, and I don't know what's going on. So they're afraid about all the sharp edges. So the question is, where's the undefined behavior? And it's going to do whatever you tell it to do. And in this case, there's no undefined behavior. I didn't tell it to do anything undefined, so it's not going to do anything undefined. This is a well-formed program. So you got to do something wrong to get your undefined behavior. So if you don't want undefined behavior, don't add that to your program. It's very simple, really. Yeah. So, we have guarantees. We have hard, strong, sharp guarantees in C++. Well-defined behavior. Don't make assumptions, just sit on the guarantees. There's no such thing as logic unless you're sitting on guarantees. The standard is very, very, very clear about what is guaranteed. You sit on that, you're good. So you can assume stuff that's not true. Undefined behavior just means you assume stuff that nobody guaranteed. If it wasn't a guarantee, you can't base logic on it. So the whole point of this is that just sit on your logic, just sit on what's guaranteed, and you're good. There's no undefined problem. You just sit on what's guaranteed. So you can try to use components. There are a lot of components out there. There's stuff on GitHub. There's stuff everywhere, and some of it's really hard to use. And maybe the APIs are bad. Maybe it's necessarily complicated, but a lot of stuff is probably unnecessarily complicated. These are all can openers. They're all can openers. Really? Do you really have to know how all those can openers work? Do you care? And I had to cut it off because there's like hundreds more. So you don't have to know everything. You just need to basically get work done. So this is kind of the lower the apprehension about when you break stuff. When your program is doing something undefined. For the most part, you're not going to break your hard drive. You're not going to, you might overwrite something. You can escape this, but this is true for all programming in all languages, right? We've got more sharp edges. Maybe we can get some lower level stuff, but we have the power probably to do more damage. But this is a problem or a concern that you might have in any language. Any language has these concerns. You got to try stuff out, you'll do something wrong, maybe stuff gets stepped on. So data objects, this is, I have a very specific view of C++ in that I'm spending resources to get work done. So if I create an int, I've spent resources and I have it, that's mine. And you instantiate them, right? Instantiation, we're defining it. We are allocating memory. I know when memory got allocated because I created something. If I didn't create it, I didn't allocate any memory. So you can define functions, and you can define data objects, and you are spending resources. So that's how you do it. Now, in other languages, they have runtimes, we have a lot of things going on. They can be spending stuff without being aware of it. So this is a contrast saying, no, I am absolutely aware of when I'm spending resources, always. So I create another one, I create an array of 100 of them, I can spend as many resources as I want. But those are all conscious decisions. That was the point. So you can instantiate whatever you want. We have virtual memory, so you can actually spend more than you actually have in the bank, right? That's the virtual memory thing. OSs will help us out with that. So this contrast, this is like a really big deal in the 80s and then the 90s, and then 20 years later we kind of forgot. But declarations don't spend resources, right? When you declare something, you didn't define it yet. Declaring something is just declaring something. That's a forced entry into the token table somewhere. Extern int my int. Is it defined? No. You didn't spend anything yet. That goes in a header. That prototype there, that goes in a header. You didn't define anything. I didn't spend any resources at all. Well, I could define it. That spent memory, right? This will end up in the text segment. The first one will end up in the data segment. But I'm spending resources when I do that. So this contrast between declare and define, this is why we have headers, right? Maybe on the day one, talking to people from other languages that don't know what headers are. Maybe you don't drill too deep into that. But we have headers because we separate the contract, the interface, from spending resources, the actual implementation. Then the linker pulls all that together. So declaring something does not spend resources. We can declare all we want. If you don't actually use it, the linker doesn't care. If you use it, the linker really, really wants it. But we know that. But people from other languages, they don't know that. This is huge. We have headers because we separate the declaring of something from the spending of resources to implement it. So, in organizing your system, there is always a concern if you're spending resources in a way that does not actually solve your problem. And C++ doesn't help you with that. Python doesn't help you with that. Nobody helps you with that. Some kind of higher level abstraction will help you with that, but this is the problem in C++. It's actually the problem in all the languages. What objects exist and who owns them, right? So in the higher level languages, there's a garbage collector. Well, I don't care who owns them. All right, well, that's fine, but you're decomposing a problem and you have referential integrity of state and data and behavior and stuff, and what exists and who owns it is how we actually break down the problem in computer science. Maybe that's too an advanced concept for other languages, but in our language we are forced to actually think about what objects exist and who owns them. That's our job. That's actually how we solve the problem. So Dijkstra and Parnas and Wirth, all this stuff from the 70s, this is how you actually solve the problem. You define the types, you instantiate the object. Spending is explicit. So your object lifecycle, that actually defines your control flow, right? When did it come into life? How long did it live and when did it go away? What did it do? How did it mutate along the way? That's it. And so if you're in a code base that's hard or confusing or a mess, your problem is here. This has nothing to do with language, right? Doesn't matter if you're Python or Java or C++ or whatever. This is why code bases, if they're hard to use and confusing, it's because this is not clear. This is always the problem. So the big ball of mud is on that slide somewhere. So data types, primitive types, fundamental types. They're defined by the language, but specifically they're defined by the language because that's the reality of the hardware underneath. User-defined types are what you the user, create to define to solve the problem, right? So integer, fundamental type. The language standard tells us what that is. It gives us guarantees on how to use it. Dog, my dog. Well, that's a type I would make, right? There's a finite number of fundamental types. We know what they are and the limits of them. We have integrals. There's one. Floats. There's one. Pointers. What kind of registers do we have? Integral registers, floating point registers, registers that'll deal with pointers. How many registers deal with type dog, type office chair or refrigerator? None of them. These are our registers. That's why we have those types. So when we deal with fundamental types, it's because the hardware only works on fundamental types. We build abstractions on top of them. It's how we construct our systems. So we make design choices. Now this is stuff we would know, but people in Python, they don't know, right? Because everything's type erased, and they don't even know what's mapping to what on the hardware below. So reasoning about real-world behavior, we can do it directly, because the language standard gives us guarantees about the behavior of fundamental types, and we compose them into higher-order domain types. So we have direct reasoning when all the reference languages, all the other languages that don't have that mapping to hardware, they will have to indirectly reason about what they're spending and how it might someday in the future map to the underlying machine. So we have a lot of hardware, it has different limitations, but this direct mapping is what we do. So the act of design is the act of lifting the abstraction of the hardware machine up into a higher level domain space, right? We build our domain types and our domain vocabulary to deal with domain problems. So here's some types, right? These are guaranteed, right? Those are the limits. These are guarantees. None of those are not true. We know what the truth is. Looks like a lot, but really we have this voidish thing. We have a pointerish thing. Heck of a lot of integerish things. And then a few floatish things. And C++11 brought us a few more. Well, it's still a bunch of integerish things. And, we have some integerish and pointerish things. And that's so that you can, kind of move your integers and pointers back and forth through some union type or something. That makes it a little bit safer. But integers, floats, pointers. That's it. There's nothing else. Optimizing for size, speed, exact bits, that's why those are there. But you don't have to use them. You can ignore them. So while there are a lot of data types, integers, floats, pointers, there are a lot of data types, but you can make it really simple. Pick the int, pick the float, you're done, right? I mean, it doesn't have to be complicated. Just use the ones that you need to use. Pick the wrong one, later on we'll pick the other one. Okay, so users, once they understand the types, they're only really working with 3 types at the fundamental level. They get kind of comfortable with that because, that's what this is saying. And then, there's a prototype. And, bool, that's a good type, right? It's a fundamental type. It's a baby integer, really. So, okay, well, maybe an unsigned integer would be a little handy. Or maybe a bigger float would be really handy. But, how many things do they need to know? They don't really need to know everything. It's like 5 things, right? This solves the vast majority of the planet's problems. You can get specialized, and in their domain, they'll figure it out really quick. So there's a debate in the community, our community, C++ community, about we can teach new programmers smart pointers without teaching them pointer semantics, yes or no? And they're, the community's a little bit exploring that question. I think the answer is no, they actually do have to know what the pointer semantics are because there are registers that hold pointers. And all the other languages are reference languages. We are a value language. So an integer holds what? And they already know this. I can do this with 5th graders. They get all of these right. An integer holds what? That. Float holds what? That. Void holds nothing, right? That's a void. And then a pointer holds, what's a pointer hold? Address. This is it, really, right? This is how we reason about the hardware. Direct reasoning that we map to the hardware below. So a pointer holds an address. Once they get that, they know integers, they know real numbers for floats, and then they know this pointer thing exists. So that's the whole point of that. So now we start getting into kind of this, how do I work with pointers? I know what an integer is, I know what a fractional real number is maybe, but how do I know what a pointer is? Well, a pointer holds an address, we just said that, but when we're talking about void, which is kind of a typeless thing, you can't really do hardly anything in C++ with a void star. A void star is actually a really safe type. Can you do indirection on it? No, right? The compiler wants type. You can't hardly hurt yourself at all, actually, with a void pointer. So using an address, at some point, you have to tell them, initializing your pointers is a good idea because that's how they're going to get bit by undefined behavior. Once you map out, memory goes from 0 to some big number. If you have a garbage value and your pointer holds an address and it's a garbage address, it's the address of something somewhere out there. What is the thing it's referring to? I don't know. It's something. It's referring to that there. What's there? I don't know. This is the dangerous stuff, right? And I find fifth graders pull this off really quick. They totally get this. They know what addresses are because they go home and there's an address, and they go to school and there's an address, and go to the store and there's an address. They're familiar with addresses. This is actually not that hard to do. So the whole idea that all addresses are just a number, they actually pick this up pretty quick. So the null pointer just says, it's kind of like a well-known address saying, you're pointing at this sort of no existent place. They get that really quick. So at some point, since void pointers are practically useless, and they are, you can't hurt yourself with them, they store an address, but you can't do indirection on them, well then you start getting into, well the point of the pointer really is so I can do indirection, and I got to know what the thing is that I'm doing indirection against. So, well, I have a pointer there, it's got a garbage address, but I think I'm pointing at an int because it's an int star, right? I think I'm pointing at a dog. I think I'm pointing at an office chair because it's a dog star, an office chair star. So that's the whole point of the type on the pointer. It's just an address, but I think I know what I'm pointing at. Now that object really isn't there, right? We didn't spend resources to get that object yet. So this is that thing where we're starting to have to explain what is the undefined behavior problem through a rogue pointer. Well, the type information gives us all the power. How big is the thing I'm referencing at? What's in there? What I can do with it? What the type system provides, right? That's all that's in there. So the address of operator is basically how we do that. So I now have a well-formed integer, and now I have a pointer pointing at that integer. Well, I think I'm pointing at an integer. It really is an integer. That works fine. And they get this. I have a cat. I point at the cat. That's totally fine. There's no red up there. That's absolutely safe. Fifth graders can do this. So now we have two ways to talk about that cat. There's only one cat. You can directly use the cat through the name of the cat, or you can indirectly use the cat through the pointer, right? Doing indirection against the cat. So reference semantics. This is reference semantics. All the other languages, C, C++, and Rust, are value languages. All the other languages are reference languages. All the other languages are doing this. So that's the fundamental thing that has been hidden from most of the other developers that are practicing professionals in other languages. They're doing this under the hood and they don't know it. So their ability to reason has been compromised quite a lot because they're being masked by a lot of the language stuff. So as we go into this, and you can see I'm indirectly bouncing the pointer around, you can follow this. And fifth graders can do this. They totally get it. So, see how, the pointer was there and now it's here. The pointer was there and now it's here. You're just changing one number. They get this. So this is really not that hard a concept. But whether or not this is a hard concept isn't the point. The point is that's what's happening during execution, right? The hardware is actually doing that. Now we can reason directly about what's happening in the underlying machine. So that's the indirection thing. Then of course the rogue pointer, this is the thing they have to know, right? A pointer holds an address, you create them. If it's uninitialized, it's garbage. If you're gonna use it, you're gonna hurt yourself. Well, that's your rogue pointer problem. Okay, so at that point, just initialize your pointers. Of course, we have references, they make that easier. Now this reference is just an alias. Still just a pointer, but it's an alias. And now at this point, the memory model is clear. This is how everything works. Everything just works like this. So no operators are needed on the reference, and a reference is just an alias, and physically it's just a pointer. It's just a pointer. We only have 3 registers, integerish ones, floatish ones, and pointerish ones. That's all we have. So references are easier and safer, use those. That'd be great. So value semantics. Reference semantics. Well, we know what those are because we're a value type language. You create an integer, that's a value. Create a dog, that's a value. Create an office chair, that's a value. And then you create a pointer, that's a reference. Or you create a reference, that also is a reference. So once they figure out that the registers and the underlying machine has direct reasoning, this isn't magic, this is how it works, everything is either down to I am doing value manipulation or reference manipulation. And ultimately, that's kind of the desired goal. This is the one thing that I think is fundamental to C++ programmers. If they can pull that off, they are totally cool. And if you don't pull that off, life is hard for a long time. But this is true in other languages too. In Python, when you have surprising behavior, it's because you thought it was one and it was actually the other. Or any other language or any other system. If there's a surprising behavior, it's because you thought it was one, either value or reference, but it was actually the other. Okay, so what is C++? It's general purpose multi-paradigm systems level language. General purpose, we kind of know, SQL would be special purpose, right? Database access, extended through libraries, domain specific concern. Yeah, we extend through, this is stuff we know, but it's general purpose. The paradigm is a really, really big deal. Big world on that by itself, but paradigm is how to think. C++ does not help you. It doesn't tell you how to think. Some things in some paradigms are trivial, but impossible in other paradigms. So we are multi-paradigm, do whatever paradigm you want. And we are like the total assembler of all paradigms. So, it's an OO language, it's a functional language, it's an imperative or sequential language. It's actually all of those things. It depends on what features you want to use, right? So paradigms map to the hardware. You have a problem space and you're going to map to the hardware somehow. But which paradigm is for you? C++ doesn't help you because it's too flexible. Other language will constrain you. Pythonic, there's only one way to do things. Perl, there are a lot of ways to do things. But if you want to mix all the paradigms in your program, it's actually not possible to do that. There are too many. If you start creating idioms and paradigms in the same code base that don't mesh well, your code base is impossible to deal with. That's the problem. Now, Python has Pythonic. One way to think, one way to work. If that paradigm doesn't work for you, that's kind of a problem. But there's only one way because it's opinionated. Python is highly opinionated. C++ is not opinionated at all. Here are the paradigms that you pull off Wikipedia. That's not all of them. There's actually a lot more that are not there. These are all paradigms, and these are real things. How to think, how to solve problems, how to break down your problems. All of those are available to you in C++. All C++ is doing is providing guarantees of the language that map to the instruction set architecture of the underlying hardware. That's all it's going to do. It is not opinionated about any of these. It's totally cool. C++ is absolutely happy for you to pick any paradigm on the wall. And given your domain, you might want to pick a different one. So system level languages, you're kind of in the systems level programming thing, mapping to hardware. That's kind of the job, right? I have a problem, a domain problem, I break it down, but ultimately it's got to map to the hardware. So, we have the tools to map to the hardware because that's what we're built to do. And then we'll have to make explicit choices on everything because every time I spend resources, that's a choice to consume a resource. So it'll be in the text segment or in the data segment, but I'm spending resources every time I do anything. So kind of the low level, middle level, that's sort of what we understand. Then these high level languages, they all tend to be reference languages. Systems level programming is in the middle, right? And so boxing and unboxing, it's a phenomenon of higher level languages because it's a phenomenon of mapping the virtual machine to the real machine, right? So if you're in the high level language, you can't reason about the underlying hardware. That's kind of what C and C++ is trying to do. That's what the spec does. It provides guarantees to reason about how to map your domain to the underlying hardware. That's really all it's doing. So direct mapping, resource idioms, zero-cost abstraction, template metaprogramming, all this stuff is, we have constructs to map to hardware. But that's basically, and you know what, most people starting out in programming, they kind of get that separation. So this idea of zero-cost abstraction is such a big deal to our community. And it is, right? Anything more complicated than f of g of x, give it a name, right? In C or C++, give it a name. And that's sort of Sean, I pulled that from Sean Parent, but you can't do that in Python. Why? Well, I'd like to give it a name, but it's going to cost me. It's going to cost me an extra function call overhead. There's going to be more work. I'm going to eat up more waste and latency by adding abstractions. In C++, those are free. Those are free. So the language standard, we have a very novel way that the compiler can optimize our code because our code is based on intent. The standard provides guarantees. And from that, we can map whatever you dream up for your solution to the problem, we can map it directly to the hardware. Not indirectly, but directly to the hardware. Because that's what the standard does. So there was overhead in other languages. Here's this is strip basically saying that the efficiency, the mapping, is what distinguishes C++ from the other languages. We have abstractions for free. So spending. Every time you do something, you are spending. If you don't do anything, you spent nothing. The more you do, the more you're spending. Conscious choices here. Our optimizations are really magic. That's why our compilers are really good and getting better all the time. The strong typing. So the type system, all logic is based on guarantees, right? If you're not sitting on a guarantee, you're doing nothing. You have to sit on a guarantee. The language standard has guarantees for the fundamental types. That'll map to hardware, the compiler, the CPU. They will respect those guarantees. And from that, we build higher order logic. We do that with domain types. We do that through the type system. So types are defined. Define cat, define dog, define refrigerator, whatever you want to do. And using the type system, we are now spending resources in a way that we can build up a domain vernacular, domain algebra to enforce invariants. We compose stuff. So the composition of fundamental things that are guaranteed into our domain is ultimately how we scale. And fifth graders actually get that. So, there's an enum, and let's compose a class there for a kitchen measure. And here's a rating, 5 stars. And there's a recipe, which is just a vector of measures, which is, units and the type to go with it. This is composition, right? We're composing higher order. Recipe box does a lot of stuff. So like the Python people or the higher level language, I can create a hash or a dictionary, depending on the language or how you want to call it, and I can just put my key value stuff in there. And it's so easy. I don't have to do any memory management. Well, I just did that here, except I have all the enforcement of the type system, right? A recipe box has a bunch of recipes, where the recipes has a bunch of measures. And this is not a lot of code, but it's all enforced at compile time. That's a form of program verification. So we have static typing. This is magic. So kitchen measures, there's a constructor, which is a contract. If you use it wrong, it won't compile. If you use it wrong, it won't compile. Oh, look, you used it right. These are guarantees. You are building domain types to build higher order of logic on guarantees. This system can't fail. So someday they may figure that out, but we know this to be true, but that is utterly novel to them. From other languages, and if they don't know any other languages, this kind of makes sense right out of the gate, because you can build up guarantees, logic. So types describe the domain, rules enforce invariants, invariants make your system do the right thing. Can't crash, can't fail, everything is verified at compile, not at run. So type checking is really nice, stuff is caught, static type checking, dynamic and static typing. Dynamic typing is very, very flexible. It is very hard to reason about because it does not provide guarantees, right? It's dynamic. It can change any time, especially at runtime. So, this is sort of, 1970s classic look blast from the past. This is highly variable. That is statically enforced by the compiler. And this is flexible, but you can't reason about it. The other one is enforced at compile. Here, you have to write runtime unit tests. Over there on the right, we have program verification at compile. So that's magic. So the majority of bugs in most any systems can actually be resolved through the type system. Why? Well, all the language is doing is giving you the ability to find your domain types that ultimately map guaranteed to the hardware. That's what the language does. But you and your domain solved your problem by breaking out domain types and invariants among the domain types. That's leveraging the type system. If all the domain invariants were maintained in your system can't crash, right? So all failed programs are based on failed invariants. The type system exists for one purpose, to enforce invariants. If it was important to you, you should have put an invariant on it. So, there is kind of this, you can be out of resources, you get an impetus mismatch in the APIs or something when you call, but we know this to be true, so much so that JavaScript's duct tape of the web, right? TypeScript is really, really popular. Why? Because it provides at least a little bit better typing than JavaScript, right? We're rediscovering the stuff we discovered 40 years ago. So this solves problems in bug count and stability and understood behavior. So we have template metaprogramming, because C++ is a general purpose multi-paradigm strongly typed systems level language. That's basically what we said. So the value semantics is a really big deal. Software's on disk. You want to run it. What happens? This is stuff we know. We know it so well that we forgot we knew it. The software image has got to be loaded or copied into memory. The OS is going to execute it. Well, to load it, it's going to be copied onto the data bus and then moved into main memory. And then when it executes, well, after setting up system resources, we'll get the instruction sequence going, and that'll start being fed into the CPU. The data instructions will be copied onto the bus, and then into the caches, and then the registers. We're going to do work. It's great. And then copies exist for each processor core because, we got cache replication. No problem because the vendor's going to take care of all the cache coherency stuff. And the mutated values are eventually copied back. And, maybe they go copy. Everything's a copy, right? This is life. Everything's a copy. There's no word reference up there anywhere. No original things exist. Everything is a copy or a mutation of some other thing. That's how things actually work. But even better than that is you have guarantees because we have localized reasoning in a lexical scope. So everything is actually sitting on the computer moving bit patterns around. And we directly reason about that because we are a value type language. So our mental model in the language and what the language guarantees is exactly the same as what really happens with the underlying machine. So all copies everywhere is chaos. This is kind of the data object and the standard and compiler. Everybody's talking about basically how to manage coherency amongst all the cached and mutated copies over the lifetime of the data object. So this is kind of the basic stuff about what is the local reasoning within a short-lived lexical scope. This is value semantic stuff. So data objects and data object values, these are nuanced ways to talk about lexical scope value semantics. Our lexical scope value semantics is how the hardware works. And if you're a fifth grader learning programming for the first time, that actually is obvious. It's obvious. It's only not obvious if you do Python or something else. So, and this is kind of the SSA assignment. So X is assigned multiple values there. There's several versions of X. How do I know which version of X is being used? Well, they're kind of guarantees in the language. It's going to use that version 1 in this case. So these mutations of values over time, this is that local reasoning that is in our code, but all programming languages are going to do it. But the big one is this contrast we have between we know when we're doing value and we know when we're doing reference semantics. And if you don't have that down, that is the thing that you have to do in C or C++, actually any language to reason about what's going on. Even in a reference language like Python, you have to understand these are different. Otherwise, the surprising behavior you can't fix. So values scale better. Reference semantics can up the computational density, but they don't scale so well. And that's why we have functional languages. So this kind of meta information really is to contrast. Value and reference is a super big deal. And I don't think you can operate successfully at scale in any language without understanding that, because the hardware is doing value. The hardware is doing value. It's always doing value. And then, whatever we compose for our systems, a lot of times reference is a tool we use so that we can, kind of share state and up the computational density. So, they know that simpler reasoning, uncoupled concerns, better optimization, better scaling. This is computer science stuff, right? This is computer science stuff. That's what value semantics for. We've known this for 50 years. Reference semantics, it is actually a tool to make sure no copies are made, right? You're going to reference some shared resources. You're not going to copy those. You're going to reference those. So, this at a high level, this is the slide. If there's no other slide you remember, if there's no other thing I say, this is the one for you. Explicit syntax. We are a value type language. That's a dog value that's passed in, wholly copied onto the stack for my use. That is by value. If in Python or Java or somebody else, it would be by reference. It's not by reference, it's value. That dog is mine in that function. The default is by value. If you don't do anything with the syntax, that's by value, because we're a value language. C is a value language. Rust is a value language. So in C++, if you want to opt into reference semantics, you can do that. You can opt in. But you do that with syntax, right? I'll pass in a reference, in this case, const reference. I'll pass in a pointer, a maybe null pointer. Yeah, a pointer holds an address, so a pointer holds the value of the address. Yeah, that's true. Yes, that's true. So these are both pointers, but yeah, that's true. So in this case here, We pass in a reference and we can mutate it, right? So coupling kind of goes up. We can pass in a pointer, might be null. So there's a little bit of red in there, but these are the variants that we have, right? In defining an API, these are our design choices. You know, what would you like your design choice to be, right? API development is hard. APIs are tough, but you could do any of those. Those are all on the table. Well, that's the safest one. The default one is the safe one. It's by value. You can locally reason. It's not like concurrently being updated by somebody else. That's the safe one. It's always the safe one. That's the most dangerous one, right? You know, that's the one that you got to watch for the most thing. Well, that's the only one that Java gives you because it's also the most powerful. So by default, the reference languages are giving you the most dangerous API by default, and you can't even opt into the safe one. We have this huge development range where we can design whatever APIs. Oh, too many choices. I don't want choices. Oh, okay, well, if you don't want choices, then you know, I'd probably just pick by value all the time if you could. Okay, so this reference semantic language, you know, it leads to inconsistencies, but here's the contrast. People that are familiar with the reference semantic languages fundamentally do not understand value semantics. That's the biggest problem I see. And then people that are operating in C and C++ code bases, they have to understand value semantics or they can't be effective. And so if I really had to pick one thing, it's the contrast between the value and reference semantics. At scale, you can't fake that. You have to be able to understand you have integers, you have floats, and you have addresses. And addresses hold, you know, or pointers. The pointers hold addresses. That's all that's going on in the underlying machine. And this is obvious when you know those three things. Everything else we do is a mapping to that. So the false dichotomy, this is just kind of fun stuff, but are we doing value compare or reference compare? I don't know. If you're a reference language, you have to pick one. And they do. And they pick the opposite one on the next reference language. So that's false in Java and true in Scala, because Scala is doing a value compare where Java is doing a reference compare, but Scala is written in Java. So how do you reason about that? So these things show up all the time. And this is the other one, the big one. You know, you can't reason about, am I doing value compare or reference compare? And that's also concurrency reasoning. Who's touching that object? Is that my object or are other people referencing that object too? You can't reason about this stuff in a reference language. And that's why they have a lot of weird idioms and patterns to kind of smooth this over. But it's all very indirect. So that's problematic. And that's why you don't get const. So this is kind of the referential transparency if you kind of get in there. But functional programming is to up the referential transparency and kind of get around some of the problems with referencing. But we're a general purpose multi-paradigm strongly typed value semantic systems level language. That's really all we're saying. Now, all of these are good computer sciencey things. Okay, lexical scope, local reasoning. So most object lifetimes are short. We tend to do localized reasoning because it's easier, safer, better control. This is computer science stuff. It has nothing to do with C++. This is computer science stuff. And as a bonus, it's actually how reality works. It's how the hardware works. It's how the compiler can do localized reasoning to do optimization. And this is how everything works. If you want to go fast or efficient, you need to do localized reasoning to be efficient with your resources, how you spend and compress resources. So we know local reasoning is good. I shouldn't have to do global reasoning over global program state. It's too hard. Certainly at scale, it's not possible. So the scope is sort of the dynamic and static scope, and static and lexical scope are kind of the same thing. So what's the lifetime of the object? And here's the dynamic scope R. Well, this totally runs fine until there's no R in the stack, and now it's a runtime oops. I couldn't resolve R, your program goes down. It was trying to dynamically resolve it. Well, we enforce that at compile, right? R, it's that R right there. I can locally reason about this. The compiler checks it, enforces it, locks it down. This is absolutely guaranteed. That's static lexical scoping. And then, of course, we have the lexical scoping. It's common in a lot of languages, but we use it a lot because we have destructors, deterministic destructors. That's us, right? Who else has that? Nobody. We have destructors, and they're deterministic. So as you kind of run down here, we can do idioms like this, because when we hit this, that'll get blown away right there. That destructor fires right there. We have guarantees. Lexical scoping, compiler-enforced guarantees. So, once they get that, there's some, best practices dealing with our idioms, but this is how the world works. The world works like this. This is direct reasoning with the compiler, the CPU, what's going to happen at runtime. What is the hardware really doing? So you have weird, funny behavior, we can reason directly about what happened. And all our fixes are the same thing. So the benefits of lexical scope, it's like no memory management, never dangling reference, can't refer to an object not in scope, it's deterministic, powerful idioms like the RAI thing. This is really cool, use that a lot. Consistent, predictable, and obvious, local context and isolation from external. You want to go parallel, this really helps a lot. And then referential transparency, improved concurrency. This is looking pretty good. That seems like a good idea. And then, optimizations, resolved at compile. You don't have to write unit tests when the compiler enforces it for you. Keeps everything on the stack, efficient scheduling. What's not to love about lexical scope with destructors? This is so cool. You should use it every chance you get. Name another language that has that. Okay, it's not the same as some of these higher order reference languages. This is, you can say that C++, but it's not. This is computer science. This is the basics of how stuff works. So we are thinking directly for how real world computation works. Because we're a general purpose, multi-paradigm, strongly typed value semantic systems level language with lexical scope and deterministic destruction, which is like super awesome. Okay, we have a single pass compiler. We have headers, right? The contract and the linker. Incremental compilation, there's some talk about modular stuff. We won't talk about that here, but headers are super cool. Because we're a general purpose, multi-paradigm, strongly typed value semantic systems level language with lexical scoping, deterministic destruction, and a single pass compiler. What is C++? It's that, right? So in the opening marks this morning, what is C++? The community, people are talking about what it is. That's what I think it is. And when people ask me, what is it? I say this. And what part of that is not a good idea? All of that is good stuff. That's good, proven, 60, 70 years of computer science, good stuff. By default, we are safer with value semantics, opt-in to reference. We have a lot more degrees of freedom. We don't pick your paradigm. We don't tell you how to think. You're going to have to do that. That's the hard work, but that's the language. Other languages, they're missing like a lot of this, which is why they can't scale. So cooking with C++, we have, kind of this idea that, it'd be nice to have something really good. And a cook gives you, a cook almost never fails you. They're giving you, Italian restaurants, they have it down, right? A lot of the standard stuff we have down. Chefs go nuts with weird things, but you don't have to start there. So a cook's conventional, may follow a recipe, maybe use stuff from cans. We've got kind of, standard ways of doing things, but it's highly, highly predictable and scalable. Chefs, well, they're unconventional. They try new styles. They experiment with fusion or whatever weird stuff they're doing. And we know a cook can do the job. And the chef, that's actually really hard because they're pushing the envelope. They often fail spectacularly, right? Because they're pushing the envelope. So you don't need to do the stuff on the right that's like weird. Most people are cooks. You're probably a little bit of both. But you want to bias your stuff into what you know works, which is the cook side. So cooks, they make good food. Chefs make great food. Predictable, unpredictable. Lots of explosions. Tends not to fail. Fails spectacularly. So if you want to go into some of the dark corners of the language where new features, promoted, and then a couple of years later we discover new things and we kind of want to back off of that a little bit, you're more on the innovation side. And if you want to actually scale and have stability and a mature incremental progress that we can rely upon, because it's based on guarantees, just do only stuff that's based on guarantees, and we know what that is, right? It's 40 years old, C++. So we know how to do that today. So it's really hard to be a chef, and even the best chefs fail a lot. Cooks generally don't. But you can't be a chef unless you've been a cook, right? Value and reference semantics. That's kind of the big one. We're a value language. The hardware is doing value manipulation. Bit patterns are moving around. And then cache coherency is managed by the great hardware somehow magically. So no matter your aspiration, solid basis, what do you need to know? And if you're 12 years old and you want to program, the type system, value and reference, local reasoning through lexical scope. You get those down, you are gold. I mean, there's more stuff to know always, but if you get these down, you're good. But the converse is true. If you miss any one of those, you're screwed. This is like you must be this tall to ride the ride. There's the bar. That's the bar. Move semantics is not up there. You can do it if you want, but that's like not required. Most C++ developers don't need anything other than this. This is what is the important part as I see it. And I find that this does actually work with new programmers just starting out. They totally get this. You just have to work on the basics. That's the basics. So conclusion, here's it is. So Qui-Gon, he's so sad. Look how sad he is. I can only protect you. I cannot fight a war for you. He's doing the best he can, but he can't do it all. C++ is not the problem. It gives you guarantees, hard, solid guarantees for you to solve any domain problem out there. But it's not going to actually design your system. You have to design your system. That's the software crisis. That's the software industry problem. It's not a language problem. It's a design problem, which can be hard. So this is the problem. So it doesn't really matter what your language is, actually. It's C, C++, Python, reference. It doesn't matter. What objects exist, who owns them, and what is the life cycle? Your problem is on that board there. That's the problem. And that's hard, right? Because you're solving real-world complex domain problems. How did you spend the resources? Are you spending resources in a way that are not helping you? Well, it'd be good to be cognizant of that. That's what this is trying to answer. So, in summary, it's easier to think in C++ because that's how reality works. The standard is a mapping to the hardware. It's guaranteed mapping with guaranteed behavior to the hardware. And then above that, you build your domain solution, your domain types, your domain invariants, your design, your system. Whatever it is you want to build, you have all the tools with very little in your way to spend resources to efficiently address the complex thing you're trying to break down. So the underlying hardware, we think exactly like it. We directly reason about it. Surprises can be explained because it's not indirect. We directly reason about it. It's more efficient to think our way because every time I spend, I know I'm spending. There's nothing spent behind the scenes. I know when I'm spending, always. So you actually do get stuff for free through the compilers and the optimization. Hats off to that team. They're just utterly fantastic for giving us stuff for free. We do have the tools to do the job. We have best practice. We have what we know for the last 70 years of computer science to be the best default practice to scale and address complexity. We have the default best practice across the board. That's a useful thing. Deterministic destruction is like a big, huge bonus, right? Can't get by without destructors. So thinking, reasoning about behavior, expressing design intent. We are trying to do real basic computer science because the problems are getting harder and harder and the complexity is getting big and bigger. And you don't want all the noise of indirect reasoning in addressing the problem. And our language doesn't have a problem with any of that. We are getting the tools to directly work off of any solution that we choose to pursue. That's why all the other languages are written in our language, right? You're going to implement pretty much everything in C or C++ or now sometimes even a little bit of Rust. So that's it. But this is the takeaway. We aren't just another language offering just another paradigm. We are all the paradigms. We don't pick. We are not opinionated. We are a guaranteed body of logic that is guaranteed to map to hardware. Go find your problem, break it down, and map it to hardware. And that's really just a blast from the past, right? That's back to the early 1970s. That's what they're saying. Bottoms up, top down. How do you map your domain solution to the underlying constraints of the engineering performance upon which you rely? So that's the bottom-up, top-down thing. C++ is that. That's its job. It directly allows you to express your solution. So in a nutshell, this was kind of the overview. The slides are rich, so if you just email them to somebody or if you want to take them and use them or get inspired to do something else, this is what I would say to people. But in commenting here in the conference, and since you're all professionals and you're going to talk to people in the polyglot world, lots of languages are around. We're doing computer science. We're not doing programming. We're doing best practice computer science. We're doing engineering. So C++ is just another language, like there are just other languages. Well, that's kind of not true. We're kind of just, these are the tools. We are just the tools in the C++ language to do the job. So any questions about that? This is my opinion on the language, which I found to be effective, especially for people coming in from other languages. Yeah. Do you think this would work in your environment? No? Too weird? Yes? Maybe? No questions? Thank you very, very much for coming.